Hi, in this video we're going to focus on understanding how to interpret the output of the regression, and there's a handful of important statistics that we need to understand what they mean. So we're working with the cereal data from the Evans book. We have 67 cereals here with the calories per serving and the nutritional information for sodium, fiber, carbs, and sugars. And what we're interested in is we want to be able to explain the relationship between the calories and the other variables in the data set. So that means that calories is going to be our dependent variable. So if we use the data analysis toolkit and run a regression, I'm going to assume you know how to do that. This is what the output looks like, minus of course the purple notes on here. And whenever I get an output from Excel, the first thing I check is I come right here to this significance F. Now you should understand that this is a p-value. I don't know why Excel chose to call it a significance F. But like all p-values, the general rule is we're looking for this to be less than 0.05 or less than 5% chance. And what that means is if it's less than 5% chance, that means that our model is better than no model. And by that I mean it's better than just using the mean of the data, the mean calories, to estimate the calories in the cereal. Technically, we're testing here whether the slope of the regression line is greater than 0. And then if that's less than 0.05, that means my model as a whole is good, statistically significant. And so I come up here to explain just how good my model fits the data. The R-squared value, it explains the percentage of the variance in the dv, the y variable, that's explained by the x variables in the model. So specifically, in this case, there's roughly 26% of the variance in calories in cereals that we can't explain by just using the changes in sodium, fiber, carbs, and sugars. And so that's probably a pretty good R-squared for cereals. Because there's still space there, unexplained variance, that means there could be other nutritional factors that we might want to actually go collect the data on and include our model. But that's a pretty good fit. This is a goodness of fit. It's how well that line fits the data. So if there's a ton of variance that we can't explain, it's kind of like a skinny person putting on really baggy clothing. It doesn't fit. That line is trying to fit really baggy data, which isn't a good thing. Once we decide that our model is statistically significant, that it's better than no model at all, and that we're explaining a fair amount of the variation in the dependent variable, then we can come down and interpret these coefficients. So these are the slope coefficients in our equation. And we could actually write the equation out. So if we're trying to estimate calories, we could say calories is equal to 0.024 times, we'll assume they're grams of sodium, plus 0.659 times the grams of fiber, plus 3.433 times the carbs, plus 3.941 times the sugars. So that would be our regression equation. And the way we interpret one of these numbers, for instance, if we take sugars, the way we'd interpret it is we would say, on average, every additional gram of sugar in the cereal increases the calories by 3.94. So think about that. If these are all in grams, sodium, fiber, carbs, and sugars, so they're equal measures, if I add another gram of sodium, then my carbs goes up by 0.024. So even if after we've done all our fitting for the model and we've decided what the best model is, there's another video I created on that. If statistically it's in the model and it's okay, statistically that doesn't necessarily mean that it's useful. So if I increase the sodium by 1 gram and it only changes my calories by just a fraction of 1 calorie, then we might choose to have sodium left out of the model, because we're really looking for our big fish here, the things that explain most variance. Same with fiber. Increase fiber by 1 gram, it increases calories by a little more than half of a calorie. And so there's a difference between statistical significance. So if we come over here, this isn't statistically significant in this model, neither is sodium. And practical significance, that's the size of the coefficient. So 2 important things to remember about the coefficient. Just because you might have a significant p-value over here does not mean that you necessarily have to keep it in the model. If your boss says, okay, tell me what's accounting for all the calories, and we say, well, sodium, if we increase sodium by 1 gram, it's going to increase the calories by 0.024. Your boss might say, really? No, I mean, we don't have that kind of precision. Let's not even put that in the model. And so we leave it out of the model. So the other thing to remember is that these are averages. They're just averages. So this is not an exact amount. So if your boss tells you, hey, I need to know how much carbs influences the calories in a cereal, and you say, well, if you add one more gram of carbs to cereal, it's going to increase by exactly 3.43 calories, you could be very wrong. Over here we have this range, and now this range is pretty tight, so we'd be in the ballpark of 3.43. But sometimes ranges are bigger. And what this is right here, this lower and upper 95%, those are 95% confidence intervals for this coefficient, which basically means if I went out to this cereal data and I took 100 different samples, 95% of the time, or 95 out of the 100, when I created a regression model from those samples, my coefficient is going to fall between 2.509 and 4.357. So there's going to be some variation in my coefficient values when I create a model from a different sample. And that's really important. These 95% confidence intervals give you kind of a range, so it gives you a sense of certainty when you actually interpret that on average, if I add one more carb to the cereal, it'll increase my calories by 3.43. You have kind of a range whether you're going to be in that ballpark or not. In fact, you could almost say, on average, if I increase my carbs by 1 gram, it's going to increase my calories from anywhere from 2.5 to 4.35. And so you could actually give a more range. And that's important information when you're making decisions. So just to review, let's go ahead and answer these questions. We're going to skip the question that our regression model answers right now. But let's go ahead and answer, is your regression model a good model for the data? This is a question of how well our model fits. If you remember, the measure that tells us how well our model fits is our R-squared. So we're going to say, yes, the R-squared indicates that sodium, fiber, carbs, and sugars explain approximately 74% of the variance in calories among cereals. Now let's go and practice interpreting each of these regressions, each of these coefficients. So let's start with sodium. So we'd say on average, an additional gram of sodium will increase the calories in a cereal by 0.0254. And if you wanted, we could even put after it, we could put the range, the 95% confidence interval. Now what's important here is notice that this 95% confidence interval includes 0. So there's a chance that adding sodium is not going to increase the calories at all. And then if we go down to the next one, we could talk about fiber. On average, an additional gram of fiber will increase the calories in a cereal by 6.659 with a range of -0.54 to 1.859. Now we could do the others, but you get the pattern here. So what's important is that you're understanding how to interpret these, that these coefficients represent averages. So obviously you should be thinking, well, why are we including sodium and fiber if they aren't significant here? But everything doesn't rest on the p-value here, and that's where you should look at the other video about fitting regression models using the adjusted R-squared. So it's really important to understand how to interpret the output of a regression model because it influences the types of decisions you make. Hopefully this has been helpful.